here I actually will have two switches. This is a set of switches. Separately, this is a set of switches. So I can take my low voltage separate. Now I have just a switch here, and I have just a switch here. And if I put them side by side, we can see that here's a switch. Separately, here's a switch. Here's a switch. Separately, here's a switch. So this can do the same thing. Let's see how it works a little differently. What we're going to do is move, the wiring is going to stay the same. We're going to move these two wires over to this. We're going to move these two wires over to this. We're going to move these two wires down here to this. Same number of wires, but I'm going to use the one that's already mounted. You can do high voltage first or low voltage first. I always like to do high voltage first, low voltage last, but as long as you keep them separate, you're going to be okay. So here I have one wire coming in, one wire coming out. Here I have one wire coming in, one wire coming out. So I'm going to disconnect these two, and I'm going to put them on the middle sets of terminal. One wire in, and one wire out. This one just fell off, which it should never happen. So that one's done. Now I'm going to move down to this one wire in and two wires out. Here we have one wire in. I'm going to put this in the very top. Coming out, two wires. I'm going to pull both these off together and put both of them on the opposite side. Now my high voltage is done. Let's just double check it. One wire in, good. One wire out, opposite side, good. One wire in, good. Two wires out, good. Now let's do low voltage. I got to move my W wire over. So here's my W wire. It's going to be on the very, very bottom side. And then I'm going to move over here, common going home. Common going home. Okay, let's see if it works. So we're going to flip the switch, connecting R to W. And if we notice, it did not work. So we got to think, what in the world happened to make this not work correctly? So what everybody does is they go through the wires, they panic, they try to see what did they do wrong. By the time they start pulling a wire, everything comes on. It did not come on immediately because this is a sequencer. It brings these on in a sequence. It also is a thermal time delay relay. So this part here is a switch. How it works, there's a little heater in the low voltage side. And there's a piece of bimetal that keeps these switches closed. Let me explain this. We have these two little porcelain rods right here, and they're white. It's going to be hard to see with the background, but these two porcelain rods keep this switch opened up. These two separate switches opened up. So they keep this open, and they keep this one open, so no electrons can pass. When this bimetal pops down, this switch closes here, and it closes here. The bimetal is just a piece of curved metal, which I seem to have lost. I must have dropped it. So there's a bimetal, which is a curved piece of metal, and this is a heater. The 24 volts comes in, doesn't go anywhere at the other side. It has to go first through this. This is the resistive element. So when we put these together, it goes through and it starts getting hot. Well, what's great about that is if you touch this, you'll feel a burn. We put 24 volts in this. This gets warm, but it doesn't get warm immediately. It takes a little bit of time. So it starts getting warm, and what that does is it warms up that bimetal. Now, bimetal is two dissimilar metals. When heated, it warps. That bimetal will pop. When that bimetal pops, it causes these switches to close. And if we were to draw it out, we would have a resistant heater here. We would have a bimetal. We would have then two rods that come up. Keeps one switch open. And then we have our second switch. It's also open. So when this heater, 24 volts, here's our W and C, gets hot, this bimetal pops down like this, which causes these rods to drop down and down, which causes this switch to drop down and close, this switch and drop down and close. It's better if you can do it in person, but what's happening is we're heating this up and it doesn't happen immediately. We can buy these in different types of heaters and different types of bimetal to have a different sequence. So when I de-energize the call for heating, notice that our lights are still on and our fan is still on. The reason this is so important to wire it through this normally closed is if the thermostat was controlling it, the fan would have shut off and our heat elements would have still been on, which would be a bad thing. In this case, even though my heat elements are still on, I'm still moving that air into the house. And it takes time, even though I've killed the 24 volts, it takes time for this to cool off. Once this cools off, that bimetal is going to pop up. When it does pop up, it's going to shove this switch open, and it's going to cause this switch to open, and this will be popped up in my horrible, horrible drawing. And that's the essence of how that sequencer is working. So we just give it a little bit of time. It'll cool off shortly, and then it will shut off. You can buy these in tons of different sequencers and times, time on, time off. When you replace them, just because it looks the same, just because you go to the supply house and you see this and it looks the same doesn't mean they're the same. You want to make sure you check these numbers. Take a Google search, Google these numbers, ask for a map of how they work or how they number them, but you want to make sure that you get the same one. This one had a pretty quick on delay, but it took a little bit longer for that off delay to happen. So we want to make sure that we set that up so we don't change that sequence. So a sequencer controls my heat elements and my fan just like I can with the contactor. Sometimes you'll see them use contactors. American Standard and Train is a very popular brand, and a lot of other ones will use sequencers. Here's what's important. What did the manufacturer decide? What did that engineer spend all of his career designing? We're going to go back with that. If we go with the contactor was there, that's what we're going to go back with. Now what's important about this is understanding how a switch is a switch. Is if you go to Mrs. Jones' house and it's on a Friday night and it's 10 o'clock at night and you don't have any more of these sequencers and you want to get her heating, you can put a contactor in and get her through the weekend. Come back on Monday with the part, swap that correct part out, and everybody's happy. So it's a switch, which is a switch. Works very much the same way. Low voltage side, don't get it mixed up with the high voltage side. Low voltage down here, high voltage switch up here. On this fan relay, here's my low voltage side. High voltage normally open, high voltage normally closed. 3 wires, it's a switch. If you want to know how that switch works, you can grab a meter. Here's one beside it. We don't know what it means. So I'm going to take this meter, I'm going to turn it to ohms. And let's check these very bottom 2 terminals right here. We'll check this terminal, and we'll check this terminal. And I'm reading about, looks like 78 ohms of resistance. So if there is resistance, we know that it's going to be a load of some type. If I check these very top 2 terminals here, I end up with OL, infinite resistance, the most resistance you could possibly happen. That means this switch is going to be open. We can see this knife blade switch. The switch is open, and I have OL, infinite resistance. Electrons cannot flow. I check between the next bottom set down here, and this, I get 0 resistance. There is no resistance. That would be this switch being closed. There is nothing to slow it down. If I check here and here, with the switch closed, I get resistance. With the switch open, OL, infinite resistance. So I know that this is going to be my load. This is normally open. This is normally closed. Here's another relay. Does the very same thing. What's cool about this relay, it's called a 9340 fan relay. It's one of the most popular fan relays out there. It has numbers 1, 2, and 3, just like we have 1, 2, and 3 terminals here. But it has a little drawing on here. Between 1 and 3 is normally open. Between 1 and 2 is normally closed. Then we have another set, 5 and 6. Between 4 and 5 is normally closed. Between 4 and 6 is normally open. So it tells you. Then we have another set over here that's not numbered at all. Let's see what those do. So we take our meter, we put it over here to the set that's not numbered at all. One side and the other. I check with the meter, firmly press against it, and I'm getting 18 ohms resistance. So that is a load. We're going to move it from this relay over here to this relay. 24 volts was at the bottom. That's my 24 volts, sorry, here and here. So we're going to move it over to what we know is a load, which was here. And we're going to move this one over to here. We're going to swap it because my wires are too short. Alternating current, doesn't matter which one's which, as long as it's both on the load side. This is the common side of my relay, so we'll put that on the common side here that's always being used. Normally open was at the top. Number 3 on this relay shows normally open, so we'll put it here. And then normally closed between 1 and 2. So on this one, this is our normally closed wire from our heater. We're going to put it on terminal number 2. So let's see how it works differently. We have a call for heat. Oh no, the heater did not come on. Now we should panic. Now we're going to wait for that thermal time delay relay. This is getting warm right here. Once this warms up enough, we're going to close that switch on, and on, just like that. No difference in operation between this relay and this relay. We satisfy our call for heat. It's going to stay on. This is going to cool off. It's going to take a little bit. We'll be off, and then off. Just like before, if I energize this relay, nothing changes. Once that system turns off, we'll try it again. I can replace this relay with this relay without an issue because it's still just a switch. A switch is a switch is a switch. This is the basic wiring for your indoor system. If I energize this, we have our switch running. It's 100,000 ways you can do this. But if you learn how to follow the schematic, understand how to read the schematic being a sequence of operation, you're unlimited. And it just takes practice. You just got to practice it. You can take a picture of this and try drawing it, highlighting as you draw. Obviously in a picture it's not going to come on, but it's the same exact thing. Here what's nice is the boards open up and you can move them between different relays, but in a live system it's going to be a little bit more complicated. And I have one right here for you to see. This is what the electric heat elements are going to look like. Just a coil of wire, resistive elements. But if we look inside, we have all of our same components. We have our letters, C, G, W, and R. We have our line 1 and line 2 that comes in. This one's using a sequencer. We have one heat element. We have our relay that controls our fan. We have our transformer, takes it from high voltage down to low voltage. We have our blower motor. So it's just like the system we have here, except it's just a little bit more compact. We use these cable ties to keep the wires nice and clean after we're done. When you're working on this, don't be afraid to cut these cable ties off. Separate the wires, follow them out. Once you're done, put the cable ties back so they look really nice and clean. Everybody looks professional, and we make some money getting people heating and cooling.